Hello everybody, my name is Vijaykumar Prajapati. I am studying in B.Sc second year, Adarsh College, Hingoli. My today's topic is Cauchy's general principle of conversion of a sequence. Before starting it, we will go through the definition of conversion of a sequence. A sequence is said to be conversion or have a limit point L if for epsilon greater than 0 there exists a positive integer m such that the condition mod of Sn minus L less than epsilon for all n greater than equal to m, which is satisfied. Now let us take a theorem. The statement of theorem is a necessary and sufficient condition for the conversion of a sequence Sn is that for each epsilon greater than 0 there exists positive integer m such that mod of Sn plus p minus Sn for all n greater than equal to m and p greater than equal to 1. Now let us prove it. Necessary condition: let a sequence Sn be a convergent and L be its limit point. By the conversion of a sequence, definition of a conversion of a sequence, there exists a positive integer m such that mod of Sn minus L is less than epsilon by 2 for all n greater than equal to m. Suppose if p is greater than equal to 1, then n plus p is greater than n and n is greater than or equal to m. By n greater than equal to m, we have satisfied the condition, so we can write mod of S n plus p minus L is less than epsilon by 2 for all n greater than m greater than equal to m and p greater than equal to 1. Now mod of Sn plus p minus Sn is equal to, now here we have subtracted and added limit point L. So we got mod of Sn plus p minus L plus L minus Sn less than or equal to mod of Sn plus p minus L plus mod of L minus Sn, which is less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. Therefore mod of Sn plus p minus Sn is less than epsilon for all n greater than equal to m and p greater than equal to 1. Now here we got the necessary required condition, the sufficient condition. Firstly, we show the sequence is bounded by given condition. For epsilon is equal to 1, there exists a positive integer m0 such that mod of Sn plus p minus Sn is less than epsilon for all n greater than equal to m0 and p greater than equal to m1. Now we take particular value n is equal to m0 such that mod of sm0 plus p minus sm0 less than 1 for all p greater than equal to 1, which implies sm0 minus 1 is less than sm0 plus p, which is less than sm0 plus 1 for all p greater than equal to 1. Now let g be the minimum value of sequence, which is minimum sequence s1 s2 s3 so on sm0 minus 1 and SM0 minus 1, and let capital G be the maximum of this sequence, that is S1, S2, S3, so on, SM0 minus 1 and SM0 plus 1. Then small g is less than or equal to Sn, and Sn is less than or equal to g for all n, hence the sequence is bounded. Therefore, by Bolzano-Weierstrass theorem, for sequence has at least one limit point, say L. Now we will show that the sequence converges to L by given condition for epsilon greater than 0. There exists a positive integer m1 such that mod of Sn plus p minus Sn is less than epsilon by 3 for all p greater than or equal to 1. Let it be equation 1. Now we take particular value n is equal to m, so that mod of Sm plus p minus Sm less than epsilon by 3 for all p greater than or equal to 1. Let this be a equation 2. As L is a limit point, there exists a positive integer m1 greater than m such that mod of Sm1 minus L less than epsilon by 3. Let this be a equation 3. Since m1 is greater than m, therefore by using equation 1 we have mod of Sm1 minus Sm less than epsilon by 3. Let this be of equation 4. Now mod of Sm plus p minus L is equal to, here we subtracted and added Sm and Sm1, so we get mod of Sm plus p minus Sm plus Sm minus Sm1 plus Sm1 minus L. So it is less than or equal to mod of Sm plus p minus Sm plus mod of Sm minus Sm1 plus mod of Sm1 minus L, which is less than epsilon by 3 plus epsilon by 3 plus epsilon by 3, which is equal to epsilon. So mod of Sm plus p minus L is less than epsilon. That implies mod of Sn minus L less than epsilon for all n greater than or equal to m. Hence the sequence Sn is convergent. Here we have proved it is a convergent sequence. Now we apply this theorem to define Cauchy sequence. So let us see a Cauchy sequence. Let's see a definition of a Cauchy sequence. A sequence Sn is called a Cauchy sequence or fundamental sequence if for each epsilon greater than 0 there exists a positive integer m such that mod of Sn plus p minus Sn less than epsilon for all n greater than or equal to m and p greater than or equal to 1. The Cauchy sequence is also called a fundamental sequence. That's for a better understanding, we take a example. Show that the sequence Sn where Sn is equal to 1 plus 1 by 2 plus 1 by n cannot converge. Let us prove. Let epsilon is equal to 1 by 2 and n equal to m and p equal to m is Cauchy's general principle of conversion. If possible, let Sn be a let sequence Sn is convergent. So mod of S2m minus Sm is less than 1 by 2, but Sm is equal to 1 plus 1 by 2 plus 1 by m. So Sm to S2m is equal to 1 plus 1 by 2 plus 1 by m plus 1 plus 1 by m plus 1 plus 1 by 2m. Then subtracting both of them, we get S2m minus Sm is equal to 1 by m plus 1 plus 1 by m plus 2 plus 1 by 2m. Now S2m minus Sm is greater than 1 by 2m plus 1 by 2m plus 1 by 2m, which is equal to m by 2m, which is equal to 1 by 2. That is mod of S2m minus Sm is greater than 1 by 2, which is contradiction. Hence, it is not a conversion. Thank you everybody for watching my session. Please like, share and comment. Thank you.